So we are going to look at problem 19 from chapter 23. So here we are given a non-conducting sphere of radius r0 that carries a total charge q distributed uniformly throughout its volume, and we are to determine the electric potential as a function of the distance r. Right? So we have a sphere of radius r0, and on the sphere there is just charge q that's uniformly distributed, and we are to find the potential as a function of r. Okay. And there are two regions. First we are to find this from r0 to infinity, in that region to outside of the sphere, and then for the inside of the sphere. And we are given that v at r equals infinity is 0. That's the usual choice. So this is a fairly typical problem, and of course it's an application of this basic formula that the change in potential between 2 points is given by this line integral. So this is the potential difference between points A and B, and you need to choose a path between those 2 points A and B and take this line integral to calculate that potential difference. This sort of question can easily be combined with Gauss's law, where you first need to calculate the electric field using Gauss's law, or perhaps the Coulomb's law, where you need to calculate the electric field, and then using that electric field you find out the potentials, given that the potential at least 1 point is provided. So how do we proceed here? Now, first of all, I'm just going to write down the electric field for various regions. So for r larger than r0, the electric field is just going to be q, this is the strength of the electric field, q by 4 pi epsilon naught r. Okay? So this is a fundamental result. Spherical symmetric charge distribution to the outside is going to act like a point charge that's concentrated at the symmetry center. Okay? So this is a result that can easily be proved by Gauss's law, and we actually in fact did prove that many times. Now for r less than r0, the electric field is going to be, let's say that q inside this point 4 pi, this is r square, 4 pi epsilon naught r square. Again, but this q inside is now not going to be the total q, but a proportionate part of q. Right? In this case, we are given that this q is uniformly distributed, so it's just going to be proportional to the cube of the radius of the sphere that we are choosing. Right? So in this case, this is just going to be q times r cubed divided by r0 cube by 4 pi epsilon naught r square, and that simplifies to q times r divided by 4 pi epsilon naught r0 cube. And again, a result that we can easily prove by Gauss's law. In fact, we did prove this by Gauss's law. So I'm going to take these as given, and I'm not going to drive these separately. Right? So with these in mind, let us look at part A. That we are to find the potential at some point outside the sphere. Now, to do this, I'm going to throw some coordinate system. This is not strictly necessary, but I think it helps conceptualizing this. It helps understanding what's going on this problem. So I'm going to look at some point on x. So this point is going to be of distance x from the center of the sphere, and this delta v, I'm going to go from some position x to r equals infinity. Is going to be minus this integral r equals, or rather, let's say this is x equals r to x equals infinity, so x equals r, x equals infinity e dot dl. Okay? So that dl is going to be just my path as I go from this point to infinity. I can just move on the x-axis. I'm free to choose whatever path that I want. So I'm just going to choose this path to be something along the x-axis, and we know that by symmetry that the electric field should also be along the x-axis. So this dot product becomes a simple product because these two are parallel to each other, and this dl becomes just dx. Okay? So let's do this. I'm going to have minus e dx from r to infinity. Okay? And I'm going to write the electric field expression here. So this is minus r to infinity q over 4 pi epsilon naught x, right? So that x is my distance from the center of this spherical symmetric charge distribution, x square times dx, and I can take this integral, and I can now write the left-hand side. So this is the potential difference from here to here. So this is the potential at infinity minus potential at some r. This is 0. Okay? This is given. This is our choice. We can always make a choice for the value of potential at one point. Here we are choosing the value at infinity to be 0. And then I can write this integral. This is going to be minus q by 4 pi epsilon naught. The primitive of 1 over x squared is minus 1 over x. This is from r to infinity. This minus cancels this one. Okay? And this becomes q over 4 pi epsilon naught. 1 over infinity minus 1 over r. This is of course 0, and now this minus cancels this one, and we get v of r is equal to q over 4 pi epsilon naught r. Okay? So not only the electric field behaves like the electric field of a point charge, but our potential also looks like the potential of a point charge, with the choice that the potential at infinity is equal to 0. Okay, now we have done this. Let's look at part B for the potential inside the sphere. So we'll proceed in pretty much the same way, except we are going to have to use a different electric field. So I'm going to now go from here to R0. So delta V from some R to some R0 is going to be minus E dot dl x equals R to x equals R0. Okay? And I'm going to, the same arguments are going to apply, that these are parallel to each other, so the dot product becomes a simple product, and the electric field has some expression that I've already written, though I think it's gone now. So let's just proceed. So this is going to be x from R to R0, and the electric field, it must be Q times R divided by 4 pi epsilon naught R0 cube, okay? Times this dl is going to become dx by the same argument of the previous part. Okay? Sorry, this is r cubed, this is x. Okay? And again, we can take this integral. It's going to be something reasonably simple. We also can write this part. This is going to be our potential at R0 minus our potential at R, which is what we are looking for. We already know this. We already calculated this in the previous part. And so we can just solve for this one. So let's take this integral. This is going to be minus Q over 4 pi epsilon naught R0 cube. The primitive of x is going to be x squared by 2. And this is from R to R0, so we can write this minus Q by 4 pi epsilon naught r cube r0 squared by 2 minus r squared by 2. Okay? And we get something very similar to, so this one is q over 4 pi epsilon naught r minus u of r, what we are looking for. So the product of these two is going to give something very similar to this, the half of it actually, q over 8 pi epsilon naught r0, and this is going to be something funny, so I can move this to the other side, or rather I can take this and move this to this side, and I can take this to the other side, Vr. So u of r is going to be q over 4 pi epsilon naught r naught plus q over 4 pi epsilon naught r naught minus q over 4 pi epsilon naught r naught cubed times r squared. Okay. And you can take this into some common parentheses. No, this is 8. Sorry. This is also 8. There's a half coming from here. Yeah, you can take this into common parentheses of q over 8 pi epsilon naught, and then it simplifies a little bit, but this is going to be your answer. Okay, so it looks a little bit different. Now, for the part C, they're asking you to plot V versus R and E versus R. I'm not going to make a full plot. I think it's in the solution manual. We can check this out, but we can kind of guess what this looks like. So for the part where we are inside the sphere up to R0, this is going to be like a parabola, an inverted parabola. The quadratic term has negative coefficient, and it's going to be shifted. For the other part, if you recall, it's just going to be 1 over r. Okay, so the sketch of u of r to look like an inverted parabola, something like this, turning into a 1 over r. And this turnover happens at r equals r0. And in fact, it's much more convenient to write all of your r in terms of r over r0. So this is just going to be at 1. And of course, at that point, we are going to have just this, v at r0. So it's much more convenient to write this as v by vr0. And this is also going to be at 1 as well. Okay? And by setting this equal to 0, you find that this is what, 3/2? Yeah, slightly larger. So this is going to be at 3/2, an inverted parabola. And then it goes as 1 over r. I don't want to do any more sketching, but this r0 is something given. Potential at vr0 is just this expression, q divided by 4 pi epsilon naught over r. Okay? And the electric field is going to look like this. This is something again we have done in class, and also this should be really familiar from gravity, right? This is how the gravity looks like inside a sphere. So this must have been done in other contexts as well, but this is easy enough. We already did this for Gauss's law. You can make a more accurate plot. Again, I think choosing r by r0 and some e by e at r0 will simplify your plot. Okay. It's going to be easier to interpret. Right. Okay. So this problem 19, can be generalized in a number of ways. And in fact, this is done in the book in problems 20, 21, and 22, and perhaps even more, 20, 21, and 22. And the basic idea for generalization is to change the distribution of charge inside your sphere. So in our case, for problem 19, Q is uniform. This is 19. And then it could be non-uniform, right? So there could be some charge distribution that depends on R, and this is what's done in problems 20, 21, and 22. Now, the basic strategy remains the same, okay? So from this, you will find E by Gauss's law. And from E, you're going to find delta V by delta V being this integral. Right? So one thing we did for 19, that because this was the charge was given rather than this rho, we were able to say that this spherical charge distribution would act like a point charge at the center. And we didn't do it that way. We actually solved this honestly by taking this integral, but we could. Okay? So how would you do this? Now, one potential difficulty would be to go from here to here. Okay? And how would you do that? So how do you go from this rho to this Q? Now, this is the charge density, this is the total charge. So you can make an analogy with the mass. If you were given the mass density and you were asked the total mass, what you will do is that if this is uniform, if the density is uniform everywhere, what you will do is you multiply the density by the volume, and that gives you the mass. But if it's not uniform, like in these cases the charge density is not going to be uniform, then what you do is that you divide your object into little parts, and you calculate the density times the volume for each little part and add those up. Okay? Now we have a name for that. The name is integral. So the Q is going to be integral of this density times little volumes, right? This capital V here is volume, not the potential. Okay, so this can depend on a number of things. For these problems, because we want to be able to calculate electric field, it always depends on just R. So we have a spherical symmetric charge distribution. So in that case, the easiest thing to do, the most straightforward thing to do, is to think of your whole sphere consisting of thin spherical shells. Okay? Then, because it only depends on R, and because all these spherical shells have the same radius, all of them are going to have the same density. So if this is R, if we can somehow calculate the volume of these spheres, then we can take this integral. Right? So let's say that our sphere has radius capital R, then this will be something like R going from 0 to R going to capital R. Right? So what is the volume of these little spheres? Well, it is given in the book. You can also calculate this. The idea is that because this is infinitesimally thin, you can actually open this up without tearing it, and the volume is going to be just the height times the surface area. Right? So this dV is going to be the height times the surface area, and the height here is just going to be just dr, and the surface area is going to be the surface area of a sphere of radius r. So this gives you the surface area 4 pi r squared times the height dr. Okay? So this is going to be r equals 0, r equals r, rho 4 pi r squared dr. Okay? And in fact, you can calculate, you can verify this by saying that your rho is equal to 1. In that case, your volume, because you have a unit density, your volume and your mass, well, in this case, charge, are going to be the same thing. So this total integral, when rho is equal to 1, should be equal to 4/3 pi r cubed, and indeed, integral of this, with this being 1, is going to give 4/3 pi r cubed. Right? So let's apply this to problem 20, just very briefly. So they're saying repeat problem 19, assuming the charge density rho E increases as the square of distance from the center of the sphere, and rho is 0 at the center. Okay, so we have a function, we have rho that looks something like this. Right, some value rho naught, and then proportional to r squared. So rho naught is some constant that we need to find it. Well, we don't need to find it, but we are going to. And this is going to be the r squared. Okay. Now, how do we proceed? We substitute this in here and set it equal to q. I think that's the easiest way. So q is going to be equal to from 0 to capital R. Well, they actually gave the radius to be r0, so let's stick with that notation. Rho 0 r squared 4 pi r squared dr. Now we get r to the 4th power. The integral of that, the primitive of that, is going to be r to the 5th divided by 5. So this 4 pi Row 0 comes out, and we have r to the 5 by 5 from 0 to r0. Okay? And so we get 4/5 pi r0, row 0, r0 to the 5 is equal to capital Q, from which you can solve for row 0. And then you are going to use this row 0 in your further calculations when you're trying to calculate the enclosed charge at a given radius. Okay, so for example, at a given radius r, you're going to take this and substitute in here. And again, this is not going to go now from to capital R, but whatever R actually you are looking at. Yeah, just like we did for problem 19. But there it was easy because this was constant. We just took this out of the integral. All right, so there was no problem there. But in general, what you need to do is to calculate the charge, and to calculate the charge up to a certain radius, the enclosed charge within a spherical surface, you need to know the row, and then you need to integrate that row up to that radius. Okay? This is how we should proceed. And then there are variations. There are 21 and 22. They just have more complicated rows, but I'm not going to look at those. You can click out the solution menu.